Hello. Now we will see the temperature dependence of resistance and the resistivity. Okay, we'll learn how the resistance of a conductor and the resistivity of a conductor will change if we change the temperature of the material. Okay, so we know that resistance of any material is related with resistivity with this formula. It is rho L by A. So resistance of a material, resistance of a conductor is equals to resistivity multiplied with length divided by cross section area, and we are talking about a cylindrical conductor. The length is L here and the cross section area is A and the current is flowing. So if we'll be changing the temperature, if we'll be raising the temperature of this material or we'll be decreasing the temperature of the material, obviously all three things will be changing. Like if we change the temperature, the resistance of the material will be changing, resistivity of the material will be changing, because you see the resistivity depends upon material and the density also depends upon material. So resistivity somehow is related with the density of the material. So when we change the temperature, density of the material changes, and which in turn will change the resistivity of a material, because you see every material internally its properties depends upon the temperature. But at the same time, when you will be changing the temperature, we already learn in case of thermodynamics, when we change the temperature, the dimension of this solid, because ultimately it is a solid. So dimension of this solid conductor will be changing. So if we raise the temperature, obviously length will be increasing, or if we decrease the temperature, its length will be decreasing. Similarly, if we increase the temperature, its cross-section area will also be increasing, and if we decrease the temperature, its cross-section area will be decreasing. So upon increasing the temperature, the dimension of this body, solid body, will be increasing, and upon decreasing it, the dimensions of the body will be decreasing. So temperature will be affecting the resistivity, it will be affecting the dimension. Okay, so ultimately it will be affecting the resistance of the material. So what we do here, we assume that temperature change is not that much. So for a limited temperature change, for limited temperature change, for a limited temperature change, we are assuming the dimension of the material remains same. So the L and cross section area, they will remain same. So we are assuming that first of all. So when we are changing the temperature, when we are calculating the temperature dependence, at that time, we are assuming dimensions don't change. So obviously temperature variation will not be that high. So when that's the case, then the temperature change will only be affecting the resistivity and the resistance. As you can see, the resistance is directly proportional to the resistivity. And if the dimensions are not changing, we can say this is the only variable. The resistance only depends upon resistivity if the temperature, these dimensions are not changing. Okay, so when we are going to change the temperature, resistivity will be changing. So let's assume the resistivity is ρ1 when the temperature is T1. When the temperature is T1, resistivity is ρ1. And when the temperature becomes T2, resistivity becomes ρ2. That's what we are assuming. Okay. So since we are assuming that at T1 that resistivity is ρ1 and at T2 the resistivity is ρ2. In that case, we get the formula. Actually, we are not going to derive that because ultimately it depends upon the internal properties. So we get the formula that ρ2 is equals to ρ1 1 plus alpha T2 minus T1. That's the formula we get. Or you can say the fractional change in resistivity is proportional to temperature change. That's the observation based formula. So when we do observe the changes in the resistivity, then at that time the fractional change in the resistivity comes out to be proportional to temperature change. Or you can say ρ2 minus ρ1 divided by ρ1. This is a fractional change. Change with respect to the initial. Change with respect to initial, it is proportional to temperature change. So if you simplify this, since it is a proportional thing, so we have to introduce a proportionality constant, and that proportionality constant in this case comes out to be alpha T2 minus T1. This alpha is defined as thermal coefficient of resistivity. Alpha is defined as thermal coefficient of resistivity. It's a local constant. So basically the value of alpha will depend upon what kind of material we are using. Okay, so if you simplify this formula, ultimately if you simplify this formula, finally we get, upon simplifying, that rho 2 is equals to rho 1 plus alpha times of T2 minus T1. This is the resistivity as a function of temperature, where rho 1 is the resistivity at T1 temperature and rho 2 is the resistivity at T2 temperature, and alpha is a constant there. Okay, so this is how the resistivity change when we change the temperature of this conductor. And now we want to calculate the resistance, change in resistance. So as you can see, the resistance is proportional to resistivity. So whatever change which is happening in resistivity, the same kind of change, similar kind of change you will assume you will have in case of resistance, because we are assuming the dimension remains same. So similar to the resistivity, the fractional change in resistance is also proportional to temperature change. And proportionality constant, when you introduce, that comes out to be same as the resistivity. So it becomes alpha times of T2 minus T1. Upon simplifying it, you get the formula that R2 is equals to R1 1 plus alpha times of T2 minus T1, where this R1 is the resistance at temperature T1, R2 is the resistance at temperature T2. Alpha is thermal coefficient of resistance this time. Earlier it was thermal coefficient of resistivity, but the thing is both are same. So this alpha is the thermal coefficient of resistance. In this case, we'll call it coefficient of resistance. And this is the formula we are getting. These two formulas one should memorize. Okay, so that's how the resistance and the resistivity of a conductor will be changing when you change the temperature. And as you can see from the formulas, if we increase the temperature, the value of resistivity as well as the value of resistance, they keep increasing. So upon increasing the temperature in case of conductor, upon increasing the temperature, the resistance increases as well as the resistivity also increases in case of conductor. So when there is a conductor and when we are going to increase the temperature of a conductor, its resistance as well as the resistivity, it keeps increasing. More and more resistance gets generated. Okay, but in case of insulator, reverse happen. So in case of insulator, if you increase the temperature, the resistance decreases there. So insulator behaves completely opposite to the conductor. We are talking about the conductor here. In case of conductor, resistance as well as the resistivity, it increases as you increase the temperature. Okay, thank you.